A specific type of statement that we want to really focus on and take a closer look at are going to be quantified statements. These are statements that include the words all, some, or none, or a variation like no instead of none. Some variation of these three terms. And so it kind of shows how two different sets overlap or interact. A couple examples here, just some numerical examples for you. Statement, all real numbers are complex numbers, okay? This is just saying that every number that's a real number must also be a complex number, and that's true. Another example, some odd numbers are prime, okay? That's also true. It just means some of the odd numbers, there's some subset of the odds that are prime, okay? There's also some primes that are odd. It kind of goes both ways in this case. And the third one here, no irrational numbers have a terminating decimal, right? So irrational numbers have decimals that go on indefinitely with no termination to them and no repeating patterns. And so it says no irrational numbers have terminating decimals. So if you think about the sets of the set of irrational numbers and the set of numbers of terminating decimals, they don't intersect, okay? So there's no overlap between them. Just give you a visual Venn diagram for each of these three statements. The first one here, all real numbers are complex numbers. So let's go in here and kind of dissect this. Let's consider each of these as a set. And typically, quantified statements, we're starting to interact the ideas of sets and logic, okay? And so the real numbers, let's call that set A, all the real numbers, and the complex numbers, we'll call that set B. All right, so in number one here, I want A and B to be two sets like in a Venn diagram, and I want, it says all real numbers are complex numbers. That means every element of A is also an element of B. Okay, so every element of A is also an element of B. All right, well, what does that look like? This definition here, this description, looks like a subset idea. And in fact, the word all typically will result in a subset. One set A being a subset of B. Okay? So this implies a subset. So when I look at the Venn diagram, we'd have set B, complex numbers as the larger set, and set A being the real numbers as a subset. Now, it could be a proper subset, or it could even be the set itself. Right? If I said all real numbers, if I said they're complex numbers whose imaginary part is 0 or something like that, then they would be equal sets. The complex numbers whose imaginary part is 0 and the real numbers are actually the same. So you can have a subset idea where they're the same. Here they're not the same set. There are complex numbers that are not in the real numbers. Okay. There is an equivalent way to write this actually. Because set A is a subset of B, it is also true that there are no elements of A that are not in B, right? Everything's in B. There's no elements of A that are out here outside of B. So I could also say equivalently, there are no real numbers that are not complex numbers. Okay. There are no real numbers that are not complex numbers. None of the elements of A are outside of B, in other words. Okay, that's an equivalent way of stating number one there. Okay. Okay. Now let's take a look at number two. I'm going to go through, kind of erase this, make a little space here. Number two, we're looking at the word sum, and again, I'm going to use two sets. So let's get rid of some of this here. All right, we're going to label our two sets A and B. So here, some odd numbers, let's call the odd numbers A, are prime. Let's call the prime numbers B. Prime numbers are numbers that are only divisible by 1 in itself when we're talking about integers. And the odd numbers, of course, are anything not divisible by 2. So some odd numbers are prime, okay? And so what that means is you might have some odd numbers that are not prime, you might have some prime numbers that are not odd, but what we do know is that there are some elements in both of these, okay? Some odd numbers are also prime numbers. That means there's got to be an intersection between the two sets, okay? So this basically means that the intersection, let's say some elements in A are in B also. It just implies that the intersection is not empty. Okay, that means they have an intersection. And so the two sets we'll call this one A and then B. There's got to be some overlap, right? Some of the elements of A also happen to be in B. All right, so they're in that shaded region there in the middle. Okay. All right, now is there an equivalent way to write that? No, I think that's what I want to keep. We'll keep it right there. Okay. Now the third one. Let's look at the third, an equivalent Venn diagram for the third one. The word no. No irrational numbers. So let's say the irrational numbers are set A, have a terminating decimal set B. So all the decimals that are terminating are set B. That'd be like all your halves, right? Because halves are 0.5, your quarters are 0.25, your fifths are like 0.2, 0.4, 0.6. Anything with a terminating decimal, if it ends somewhere, those are not irrational numbers, and irrational numbers are not terminating decimals. That means the intersection is empty. Okay, it means they're disjoint sets. So if I were to take, I'm going to rephrase this in set form. There are no elements of A that are in B. Okay? No elements of A that are in B. That means there's no intersection between the two. So my Venn diagram would simply show two disjoint sets. Okay? All the irrational numbers are over here, all the terminating decimals are over here, and there's nothing that overlaps the two. All right. Now, let's take a look at the negation of each of these statements. Okay, the negations are a little bit interesting. And we can kind of get some idea based upon the corresponding Venn diagram. Okay, so going back to statement number one here for the negations. If statement number one, let's say that statement P, then what I want is statement not P. What does that look like? Okay. Well, if all real numbers are complex numbers, right? So you have this Venn diagram. Oops, I got those reversed. Where A is a subset of B. So the original statement here is essentially saying, remember, complex numbers were B, real numbers were A. The original statement there is saying that A is a subset of B. Okay? And so what we need for its negation is just to say that A is not a subset. Well, if you were to take this set A and slide it out, as long as it has some element outside of B, you've negated the statement. Okay? So as long as there's something in A that's not in B. So the negations, and I'll use the little squiggly line for the negation here, is either going to be a set where A contains elements that are outside of B, right? Or it could be the case that they're completely disjoint. Maybe there's no intersection at all. Okay? And so what I want to do is make a statement that, make a sentence that describes these two together. Okay? Well, basically, as long as there are elements of A that are not in B, or here there's elements of A that are not in B, then you've encompassed both of these situations and effectively negated the original. So what I could say is, there is some real number. Well, let me do it in set form and then we'll translate it. There is some element of A that is not in B. That would be the set notational way to, or the set form of that statement. But we're to translate it back into the real numbers and complex numbers. The negation would be, there are some real numbers that are not complex numbers, right? There are some real numbers that are not complex numbers. Okay. That would be the negation. Now, of course, one of these statements must be true and one of them must be false. In all three of these cases up here, I chose the true statement to write. So here the negation would be false. Okay, that's not always the case. I could have written a false statement up here in which its negation is true. Okay, so, but in this case, I've got three true statements. So we're going to end up with three false statements. Okay. All right. So that's the first one. There are some real numbers that are not complex numbers, would be the negation. All right, let's take a look at the second one. Here again, let's do the odd numbers are A, prime numbers are B. And in this case, let's call this statement Q. Okay, statement Q says some odd numbers are prime. So what I want is, I want to find not Q, okay? Remember, Q basically says that A intersect B is not the empty set. Okay, A intersect B is not empty. That was what we determined there. They have some overlap. Now it could be the case that A is a subset of B. That's possible. But we're just looking to make sure the intersection is not empty. So really, when we say some odd numbers are prime, we're looking at Venn diagram, and I wrote one up just a moment ago where they intersect, right, A and B. But it could also be the case where A is inside of B. That's possible, as long as the intersection there is not empty, right? It could even be the case where they're the same set. That's all right as well. So these are some options, but definitely have to have an intersection there. They can't be disjoint. Well, what's the negation of that? They would be disjoint, right? So the negation would say no elements of A are in B, right? So if I form the negation, the Venn diagram would just be disjoint sets, right? So the negation basically is that the intersection is empty. If the intersection is not empty as my original statement, then the intersection being empty would be its negation. That means they're disjoint. So I would say that no odd numbers are prime. Okay. Okay. So it's not the case that some of the odd numbers are prime, meaning no odd numbers are prime. Okay. So that's the second one. And now let's take a look at the third one, to negate a no statement. So here, let's call this statement R. And remember, with no, when we have a no statement, no irrational numbers have terminating decimals, again, here's A and B, we determine that that means their intersection is empty, right? So here we'd say that A intersect B is the empty set. Well, if I want to negate that statement, I'd have to say that the intersection is not empty, which is going to look a lot more similar to number 2 here. And so, let's see. So in order to negate the case where A and B are disjoint, you have to turn it into a case where they do intersect. And of course, you could have this sort of case. You could have A as a subset of B. You could even have B as a subset of A. It doesn't really matter. You could have them the same, as long as their intersection is not empty. Okay. And so the negation then would say A intersect B is not the empty set, which means there's got to be some element in there, right? So there is some element of A that is in B. There's some element of A that is in B. All right, so now put this in the context of the third statement here, we would say there would be some irrational number with a terminating decimal. Okay, that's the negation. There is some irrational number that has a terminating decimal. Okay, so that would be the negation of the original statement saying there are no irrational numbers having a terminating decimal. Okay. Okay, so that goes through the 3 different types of quantifying statements. An example of each gives you kind of an idea with the Venn diagrams how the corresponding sets interact in terms of their intersections, and then it also shows you that what the negations would be like. Generally speaking, the negation of a some statement will be an all statement, and the negation of an all will be a sum. Also, the negation of an all statement will be a some are not statement. Okay, so it's a little bit different there. So if I were to say, as an example, some A are B, the negation of that, if this is P, then the negation of that would be no A are B. Okay, and if I were to write my statement, if P was all A are B, then the negation of P would be some A are not B. That word are is very hard to read, isn't it? There we go. So all, the negation is some, the negation is none. Oh, I'm sorry, all the negation is some or not. That's it. So you got the some, but you also have the not there. And then finally, if the statement is no A R B, then the negation of that is going to be some A R B. Okay, so that should give you a quick summary of the three different types of quantifying statements and their corresponding negations.